Let us now discuss how it actually works. Basically, we feed in a clock pulse into the sequential circuits and the work alongside that. So you might actually wonder that what is a clock? Is there anyone who can tell me what is a clock? We view this as a time keeping mechanism, right? Isn't it? Hello, guys. Okay, who said no, sir? What do you think of it as? Clockwise spins? See, basically, we look upon clock as a time-keeping machine. More specifically, we keep it as a timing machine, right? How does it actually work? Through periodic signals. That is what the clock is about. All right. Now you see, a clock gives us periodic signals, but not necessarily those are even. Not necessarily those are even. They may give out signals like this, but the periodic in nature, some way, but you cannot use them. You cannot use them for timing purposes. Why? See, look at the beat that I'm giving you. See, this is a beat, right? When you are marching, like when you're marching past, so when soldiers march, they are timed by their bands, right? You've seen them? The bands going, right? This is periodic. These bands, they act as the clock. How are they acting like a clock? See, this is periodic, right? So now you can say that when it goes like this, left foot, or when it goes like this, right foot, left, right, left, right, left, right, left. So it can be made faster. Periodic. So left, right, left, right, left, right. So why are we doing that? Because individual soldiers need to coordinate in order to march. Correct? So individual soldiers need to coordinate in order to march. So it's not just the band. The march past master also goes ek do ek do ek do ek. What is this? Clock, timing. So when you are hearing me, all of you are here. Let's say I ask you to march. Divya will be doing left right in her own way. Briganko will be doing left right in her own way. Somnath will be doing left right in her own way, etc., etc., etc. But if one of you act as the captain, he or she will be the clock. Or let us say I am the clock, I am the captain, and I'll be saying ek do ek. So when you say ek left, do right, ek left again, then after that you put a right, then again ek, then go left, right, left, left, right, left, left, right, left. And I am telling you this. Why am I telling you this? So that you can synchronize your brains with me, with my sound. It's a very important aspect that you all have seen, but you need to understand. If you don't do that, what will happen? Divya will march faster than Mriganko, will march faster than Somnath, will march faster than Shilpa, etc., etc., etc. It will not be a march fast, it will be a chaos. So it will just be walking. It will not be marching. It will just be walking. Everyone has gone to the park to march. Everyone has gone on the streets to march, not marching, but walking. When you have it's a specific march, everyone puts the left foot, right foot, left foot, right foot, everyone. Just like we do in the army. So when you see, have you seen Kuch Kawaj on 26th Republic Day parade? You see that? So it looks so good, right? It looks so good, isn't it? For example, let us go into wartime now. If you see wartime movies, you will see all the guns firing, bum 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 bum, then again bum 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 bum. How? Timed, in a timed way. Left, right, like so. One, two, three, four. Fire one, fire two, fire three, fire four, fire five. Then okay, someone has died, someone is important, like a soldier or a policeman or a fireman or someone who is like a politician, or someone has died, they give a gun salute. Take aim, fire, bam, fire, bam, fire, bam. 21 guns, three times fire they do, or something like that. They do it at the same time, exactly at the same time. How do they do that? Clocking. How do they clock it? This order: fire, fire, fire. Everybody is hearing fire, bam, fire, bam, fire, bam. Right? So this is the clock that you need to hear. So then, similarly in a computer, there are so many different types of devices. Sometimes they need to work in parallel with each other. Sometimes they need to work in conjunction with each other. So circuit 1, then circuit 2, then circuit 3, then circuit 4. What happens if circuit 1 has not stopped working, circuit 2 comes up, no input? Understand this? No input. Before feeding in the carry, if you feed in addend and organ, before feeding in the carry, what will happen? Carry will not be added, isn't it? There will be an error, or at best, if your system is that fault tolerant, it will allow an erratic result because the carry has not been taken into consideration. But you have to put in the carry with the addend and the organ to get a total addition. So it's called a full adder, total addition with the carry. Do you understand me? Cut to something else. Let us say you are storing a variable's value in the memory. Okay, you're storing a variable's value in the memory. So let us just have a diagrammatic representation of how that happens, or just a logical diagrammatic representation. Let us say you have an adder circuit. It may be a parallel adder, serial adder, whatever. It is adding a number. This number here is added. The sum. It takes two numbers and adds, and etc. So now this needs to be taken to the memory. So first of all, you need to enable the memory. Secondly, you need to give the address, that is the location. Now you guys have all done C. You know what memory addresses are. These are the lines in memory. Each of these are capable of holding a number, and the location of a data on memory is called the address of the data, right? So when you enable it now, when you so that means that you need to store it in a particular location. So these may be like this 0 1 2 3. I'm writing in decimal. These are obviously not in decimal. These are actually in binary or hexadecimal numbering. So first of all, you need to enable the memory's input. Then you need to give the particular address where you want to put that value. Let us say it is 0 first. So need to first enable the memory. They need to give the address 0. That means that you are activating this part for input. Then you need to pass the sum, and the sum is written here. Then you send the sum. The memory has been enabled. The memory has chosen a particular address according to your liking. The memory has chosen a particular address. Either it could be provided by you or your program. It has provided, it is chosen a particular address. You give the sum goes into the memory chip. In the memory chip there are so many different lines, but none of them are selected, only one is selected, and the input buffer is on, so the sum goes in there. What is the input buffer? The input buffer is a sort of a digital logic. It is sort of a digital logic that allows you to input something into the memory. If the input, or not just memory, any device, if the input buffer is off, you cannot input anything. If the input buffer is on, you can input something. So the input buffer has to be enabled. Then you give the particular address that is chosen there. All the others are off, this only is on, so the sum comes in. Where does it go? Nowhere else to go but here, so it goes in there, and sum here, as you can see, is written as it is. So if the sum is x, this is x written in memory. So we say that in C parlance, we say that ampersand x equals to 0. That means the address of x is, or rather ampersand x is double equal to 0, beg your pardon. So ampersand x is double equal to 0, which means that the address of x is 0. That's what we say. Now how does it do that? Because we enable the input, we give the particular address which is then selected. When the sum comes in, when the data comes in, basically this is nothing but data. The data comes in through something called the data bus. The database is nothing but a sequence of lines that comes in with data, or that brings the data in. So when the data bus brings in the data doesn't find anywhere else to go. There is nothing anywhere else to go. It just rushes into the selected place, which is the 0 line. Doesn't have any other choice. In all of these, you can see, let us say, change the sequence. So let us say, what is the sequence? Enable, choose address, input sum, disable, because you want to close the input buffer so that nothing else can come in. What will happen if you don't do that? Then whatever you have put in will be overwritten with the next number. Now if you see, if you change this sequence to this, choose address, input sum, then enable, disable, do you think this will work? Do you think this will work? No, obviously not, because you haven't first enabled it, then you have to choose, then you have to input it. So this is a sequence, otherwise it won't make sense. When the sum comes, input bus is disabled, it will be lost, it won't be able to go in, it won't be able to go in. So all of these is just like left right left, left right left, left right left, like that. So that is why, how the signal flows in. First pulse enable, what pulse? Clock pulse. We talk about clock pulse. You see, these are nothing but pulses. So the first pulse enable, Second pulse, choose address. Third pulse, bring the input. It may be third pulse or third several pulses. It may take one pulse, two pulse, three pulse, whatever pulse it is. Let us say that you are putting in a 16-bit number. So in the 16-bit number, and if you are bringing it serially, and each pulse brings in one input, then you will need 16 pulses. Or conversely, if it is parallel, then it will happen in one pulse itself. Then the next pulse after the input is over, disable. Now your data is secure here. Nothing will overwrite it. Unless and until you do this operation again, nothing will overwrite it. It won't be lost. As long as we're talking about, say, RAM here. If it is RAM, random access memory, you know, whenever the power is on, the random access memory retains its value, so the value is there. Safe and secure as long as the power is there. If it is ROM, on the other hand, a hard disk, then it is secure even when the power is off. Correct? So you see, this is how timing is very essential to memory, to other things also. When you're printing, when you're interrupting, all of these that we will talk about later on. Sequencing is very necessary. What will happen after what? What will happen now? What will happen next? What will happen then after? Very necessary. And what will give you that timing sense? That timing sense is given by the clock. Now this, you see, if this is going to happen like this, you have to equally distribute it. For example, if I give you a clock like this, this is also a clock, but you cannot march to this. Why? Because here the periodicity is not very harmonic at all. This is harmonic, or left right, right? It sounds better. Why? Because it is harmonic in nature. I'm maintaining a certain amount of gap, a certain amount of time period. So that is how, when we are talking about clock pulses, the clock pulses that will be of use to us basically look like this, even, or let's say this, even. So evenness in periods is very necessary. However, we are talking about digital logic circuits, right? So these are analog curves, but we are talking about digital logic circuits. Digital logic work with a 0 or 1. Here we talk about digital curves like this. Sorry, not like this. I beg your pardon. Like this. Like this. So even curves. This is a digital. Why digital? Because we are not considering all these values. We're considering only this value, that value, this value, that value, this value. So you can put it as a 0 and a 1, 0 and a 1, 0 and a 1. So in other words, if the pulse basically looks like this, either like that, it will be able to, it's a very good thing. Otherwise, it can also be some other periodicity like this, etc. So this being ones, conventionally, you can take this as 0 if you want to, but Generally we take it as 1, this being sorry, these being zeros. Here zeros are smaller than 1, so basically that means that clock goes up, stays on 1 for some time, comes down, a little period of time it stays on 0, goes up again like this. You can have conversely this pulse also. So here goes up, stays for a little time, then comes back and stays on 0 for longer, etc. But these are all periodic, and the periods where the time periods are identical. The time period, so basically we are talking about normally what we consider time period, the time between these two. For this, so basically this is like on time. So time period, this is nothing but on time plus off time. Well, actually this can be misleading, so I will just say 1 time and 0 time, because as I said before that 1 and 0 are not exactly on and off. It will be on and off definitely, but it not exactly is 0 volt and a 1 volt or something like 0 volt or 5 volt, something like that. It is a above threshold, this is above threshold, this is below threshold. So above threshold time plus below threshold time together is the time period. So this, then this, then this, and here it is this, and here it is this, then this, it's like that. So basically here this is twice the on period or the twice the off period, because they're very even signal. This here so is obviously we have to consider it as on plus off. Here also on plus off, because this is a multiple of this. It may be a fractional multiple of this also, and it is not exactly the same, so we cannot do it as twice the on period or twice the off period. This won't give it this. In any case, the generic sequence is 1 plus 0 time, so 1 time plus 2 time, 1 plus 0 time, sorry, on time plus off time, on time plus off time. This will give you here also on time plus off, except that in this case on time plus off time is twice off time or twice on time. Because now you see, when we are going for a clock, a digital clock, when we are going for a digital clock, a wall clock, this is what we require. Because seconds, 1 second, 2 second, 3 second, 4 second, as soon as it is on, or it can be this one also. Actually, in a digital clock, sorry, beg your pardon. In a digital, in a wall clock, it will be this, most likely to be this. Okay, why? Stay off for 1 second, then come up, move the second hand. That means there are 3 hands on a clock: hour hand, minute hand, and a seconds hand. So it will move the second hand, come down, stay on for 1 second, go up, move the second hand, come down, stay on for 1 second, go up, move the second hand, come down, move like this. This or this, where this, either this is 1 second or this is 1 second. This is for a wall clock. This, on the other hand, if you use it in a circuit, needs to come on or go off in equal time period. Then you need something like this: on for some time, off for the same time, on for some time, off for the same time, on for some time, off for the same time. And all three signals are used in computer devices. Not just all three, these there are different types of the three basic types. There are all different types of digital signals. All of them have to be periodic. Periodic obviously, but then all of them have to be digital, and the time periods have to be even. Whatever time period it is, has to be even. Okay. For example, theoretically speaking, we can say that there can be a signal like this also. Then, okay, you can use this as a signal, like that, etc., etc. That to be even. Whatever it is, the repetitions have to be even. So these are all repetitions, right? So the repetitions have to be even, like this. This is one type of repetition. The other type of repetition is another type of repetition, another type of repetition, like that. Repetitions. They have to be even. When you do that, when these pulses are used for working with the circuits, we call it synchronizing. When these synchronize with the circuits, but then we can sorry, when you're using with this kind of pulses, we can then synchronize the circuits so that, for example, this one will trigger circuit 1, this one will trigger circuit 2, or this one will trigger the circuit 1, it will start, take it off, then put it on, take it off, then put it on, put it off, put it on, put it off, like this. We can use it like this, for example, that here some circuit is on, then this is off, while this is off, some other circuit is on, then again this circuit comes on, then the other circuit turns off, then again this circuit is on, that circuit is off, like this. We can time it. Different clock pulses can be used for the timing of devices. And timing of devices, as you just seen with the example of the simple memory exercise that we did, it's very important to time the devices. Now you see, devices which are synchronous, syn means same, chronos refers to time, from chronos, synchronous, same time, the timing is the same. So basically the time, not doesn't actually mean the timing is the same, actually means the timing is matched. Let us say it like this, the timing is matched. So one is slow, one is fast, that is fine, but their timing is actually matched. So the timing is actually matched. So this is your synchronous circuit. Now with synchronous circuits, the triggering can be of two types. Let me show you. So when you have a synchronous circuit trigger, triggered by clock, by clocks. Now you see, when you are talking about a clock pulse, digital clock pulse like this, some devices are turned on and off by either as 1 and a 0 and a 1 and a 0, etc. These are called levels. So devices changing state with 0 or 1, okay, levels are called level triggered devices. Similarly, these are called edges. This is the positive edge because it's going from 0 to 1. This is the negative edge because these are called, because it's coming from 1 to 0. Now there are devices synchronized by changing clock pulses, or rather by when the clock pulse is changing. So when the clock pulse is changing, that means it is going from 0 to 1, then it is triggered, but it's going from 1 to 0, it is triggered, and it's called an edge triggered device. Edge triggered device. The device changes when the edge is changing, works, and then when it is coming to a level, it is stable. It doesn't change. It's an edge triggered device. An example of level triggered device that we'll see are latches, the simple circuits, like for example SR latch, D latch. Edge triggered devices are flip flops. For example, more complex circuits, edge triggered devices. Edge triggered devices are slightly complex. As you can imagine, they have to work according to an unstable signal because it's unstable from 0 to 1. It's stable at 1, stable at 0. It's unstable from 0 to 1. When it is edging up, it is working, or when it is edging down, it is working. So the circuits will have to be a bit more advanced. These are relatively simple circuits.